be recorded. But we're going to talk about different parts of it, why the different parts are how they are. The first thing I want to talk about is actually the fact that a polynomial, the shape of the polynomial. Polynomials are continuous and smooth. All polynomials are like that. What continuous means is, and this is something that you get into in calculus a lot, continuous means that if you put your pencil on one end of the polynomial, you can trace along it without ever having to pick up your pencil. So your piecewise functions, a lot of those were not continuous. Because as you were drawing, you may have to pick up your pencil to go start tracing it at another point. But all polynomials are continuous. Smooth means that you don't have any corners. Absolute value is not smooth, because absolute value has a point. But all polynomials are smooth functions and they are continuous. So that's the first thing. There's actually definitions for that. We're not going to get into that, but there are definitions that you can prove just like you do proofs in geometry. And then off those proofs, you can build more and more things about functions. If in college you go farther in math, that's kind of an advanced calculus class where you do all those proofs. So if you hate that kind of stuff, that's where you steer away from those kind of classes. All right, so the next thing we need to talk about is this part. This is called the end behavior. Polynomials always have a middle section where they have a bunch of bumps to them. You know, weird things happen. But after the bumpy part, then eventually they start going off in one direction, and they will continue in that direction forever. Nothing ever changes. And it becomes pretty much like a line. That is called our end behavior. And we have specific rules where we can actually define the end behavior without ever looking at the graph. We can just look at the equation and we know the end behavior of the graph. So that's our next part. We're going to actually define that. So hopefully you've had a little bit of this in Algebra 2. So this, I'm not expecting you to know this off the top of your head, but hopefully as we go through this, this will be a little bit of a reminder. Hopefully it's not just brand new. Okay, so if we have a polynomial, so we had this general formula the other day. Now, I don't care about any of the rest of it. Whenever we're talking about end behavior, the only thing that matters is that first term. All we care about is the degree of the polynomial and the leading coefficient. So, our degree, when we're talking about this, degree is n. Leading coefficient is a sub n. Okay. Hopefully I'm going to give you ways of thinking about this so you don't just have to memorize the rules, but if you're the type that you like memorizing rules, great, go for it. Okay, we're going to start with your power, or your degree. So we have two ways of thinking about this. Your degree can either be even or it can be odd. Now, if it's even, think about a parabola. A parabola is even. It has an x squared. What is the end behavior of a parabola? Yeah. Parabolas always go up and up or down and down, correct? So, a parabola always looks like this or like this. So, wherever you have an even power, they always end up going in the same direction. Always. Okay, so it's even. So next thing we look at is our leading coefficient. Okay, if our leading coefficient, now, what makes our x squared, what makes it go up? Or negative or positive. So it goes up if it's what? Positive. So if it's negative, it goes down. If it's positive, so it goes like that, right? So if it's even, they go in the same direction. And if it's positive, it goes up and up. If it's negative, it goes down and down. Okay, so odd would go in opposite directions. So you can think of multiple things with this. Easiest one would actually be a line. A line is an odd polynomial. So here you would just be thinking about slope. So a sub n would just be slope. So if I have positive slope, what happens to the left-hand side? It's going down. And your right-hand side is going up. And if I have negative slope, it's just reversed, right? So there's your rules for end behavior. Kind of like a flow chart. You have what your thing is, and you follow your flow chart until you get what you want. Now, this isn't the actual way of writing it. This is usually how I write it. I am totally okay with you writing it this way, because this is how I'm presenting it. The actual way of writing it is saying stuff like this. So this is the way of writing this last one. As f of x, as x goes to negative infinity, f of x goes to positive infinity, and as x goes to positive infinity, f of x goes to negative infinity. That's the technical way of writing that last one. That is a lot of writing. I don't like writing, so I'm okay with you writing up and down. any way you can convey to me that the left-hand side goes up and the right-hand side goes down. So that's what this means. This means x is on the left-hand side because it's going to the negative infinity side. My y value is going up. As x is going to the right-hand side, my y value is going down. All right, so if I do a couple examples of that, am I okay? Switch. So our goal at the end of this is to be able to take a polynomial and graph it. So what's the end behavior of that? Up, up. Again, wherever you're looking at this, none of that even mattered. All that matters is the first thing. Degree is even. Leading coefficient is positive. Are you okay with that? Josh, you're driving me crazy. Exactly. Okay. Next part that we need to talk about. Are these points here. Okay, these are your x-intercepts, which again your book likes calling zeros. They are also your zeros, but on a graph they're x-intercepts. What happens if you have a zero that's an imaginary number? Well, if you have a zero that's an imaginary number, it's not an x-intercept. It creates a curve that is up here. So that's why zeros and x-intercepts are different. You can have a zero that's not an x-intercept if it's imaginary. Now, the issue is whenever we're graphing, we have no idea where those are. You can tell whenever you get farther on in calculus. You can find those. For what we're doing, we can't. So we're not concerned about them at this point. We're only concerned about these. I know. We're getting close. So what we're going to do is I'm going to show you guys how to find them, and we'll call it quits, and we'll finish it up tomorrow. All right, so what we're interested in is just how to find them. Now, we're not going to spend a whole lot of time on that because you guys have already done it. So we can find zeros by doing things such as factoring. Completing the square. Quadratic formula, which is really just completing the square. I don't think I ever showed you that. Simply solving for x. Isolating the square. Factor by grouping. Some difference of cubes. Okay, problem is all those are restrictive. These up here only work on quadratics. This only works on linears. This only works on cubes, special cubes. This only works in special cases. So all of this is very limited. So on your problems that you're going to be given, you're going to be asked to find some zeros. You're going to be asked to find zeros in very limited cases. In the next section, we're going to learn how to find zeros in broader cases. Those are the ones where you do, well, first we're going to learn how to do long division and synthetic division. Then we're going to do the P over Q stuff. P over Q is still kind of a special. There's still cases where P over Q doesn't work. So we'll stop there. We'll talk about zeros a little bit more. Then we will actually do some graphing, and then we will do one more thing. So we'll finish that up tomorrow.